Hello.
Are you there? I cannot hear you. Pedro, are you there? Send him a message.
Okay, so I'm gonna start. Thank you for the introduction. I hope it was good. I didn't hear it. Do you hear me good? Just say okay. Okay, very good. Excellent. So I'm gonna present some work on flow instabilities over hypersonic cone-cylinder-flare model. So this work is kind of follows a typical scenario for us in which we have a problem we don't understand. There are some experiments doing some measurements that we would like to understand the physics for that. And then we attack with everything we have numerically with the computers and theory to see if we can explain what's happening. And then we can extrapolate those now this new theory or this understanding for the physical mechanisms to flight and for design. So in this case, I'm focusing on this cylinder flare that we've been working for a couple of years now. My name is Pedro Paredes. As Marcelo probably has mentioned before, I'm in the National Institute of Aerospace as a NASA Langley contractor. So my office is inside NASA Langley, and I'm through the National Institute of Aerospace. And thank you very much for the invitation to this symposium. Okay, so now I'm gonna use this little hand as my cursor, so you can, if I need to point at something, you will see this hand there. So this is the research team that I work with. We are all resident at NASA Langley. So from NIA, this NIA NASA Langley contractor thing is myself, Balaji Venkatachari, and more people also collaborating with this. Milan Chowdhury, Fei Li, Nathaniel Hildebrand, and others are civil servants at Langley, also that have been helping on this work. And I have a couple of PhD students working with me. One is through UMD, the University of Maryland, and the other one is through North Carolina State University. They are Connor Klaus and Anton Solt. All right, so let's continue. So the outline of the presentation is some motivation why we do these transition studies, the measurements for the cone-cylinder-flare, what we would like to understand, the objectives, and then the strategy of how we want to do those objectives to understand the measurements, then some slides about the theory that we use to do these things, and then the results. So I hope it's not going to be too much for you, but you can always read some literature about it and kind of have kind of a motivation of how we do these things and what we get out of that. And then you will see a summary and concluding remarks, and I will be open to any questions or discussion or anything you would like. Okay, so starting with the motivation. So transition to turbulence happen when you go from a laminar flow, something of this order, like in this smoke buoyancy driven flow, and then you get to the turbulent or chaotic flow. And there is a process for that, and you will see here some kind of an order structure is almost periodic here. And that's what we are trying to understand, how to go from laminar flow to turbulent flow, and we would like to understand this process. So the laminar turbulent transition is a complex physical process, critically depends on the disturbance environment. It's difficult to classify into sub-processes. It's parameter dependent, and it's important for design of fluid system. By fluid systems, I refer also to vehicles like aircrafts, helicopters, or anything that flies, or even in the water too, a submarine, boats, anything with fluid around. Okay, so this is a very nice picture by Kobayashi in the 1980s. It's a cone, a rotating cone. So at the beginning, close to the nose of the cone, you have laminar flow, and then you start getting some kind of streaks. And those are as a consequence of linear instabilities, in this case, cross-flow instability that grows, and then it breaks again. You have now these kind of structures in top of that, and at some point you get the turbulent flow or chaotic flow. So this is actually kind of from laminar to turbulent is super similar to this flow here, the buoyancy-driven flow, but in this case, just the smoke, and the other one is in the boundary layer over this cone. In this case, we are not rotating, it's just the flow over this cylinder, and also in a flat plate. And what we get now is, again, is a sequence of linear instabilities. They grow, and then they break down to turbulence. So we go from laminar to turbulent again. And this is what we need to understand to have a good design of the vehicles, and also the performance, how they fly, how much resistance to the air they have, and the lift, and so on. So why we could just do a big simulation of all the transition process, but for that we need to know all what is coming in, everything from the free stream, also the roughness and everything. So why we want to model transition is very important for the future, to be able to apply this modeling and apply transition theory to design of real vehicles. The laminar turbulent transition is accompanied by a large increase in skin friction and surface heating. And the transition prediction is a critical element of the CFD process for multiple aerospace vehicles across the speed region, everything from very low speed to very high speed. According to the CFD Vision 2030 study, it's a big NASA study trying to understand what we need to be able to use CFD for design and avoid a lot of testing in aircraft design. Is that the basic set of capabilities must include at a minimum the emphasis on physics-based predictive modeling, and also a higher degree of automation in all the steps of the analysis process. And we know that modeling, instead of simulating transition, will reduce the cost estimates for LES by 10, 100, or even 1,000 times, actually. And the eventual goal is to have a reliable transition modeling for aerospace applications across the speed regime, vehicle classes, and the operational envelope. So now we are getting more into the different mechanisms and more focus. So what are the mechanisms for this transition to turbulence in boundary layers? Now I'm focusing now in boundary layers for aerodynamics. So we can have very multiple instability mechanisms to get to transition and to turbulence flow. So in 2D axisymmetric boundary layers, we will have what we call the planar turbulence lifting modes. That's for subsonic flow. And then we have what we call the max oblique first modes and planar second modes. So it's all instability modes in the boundary layer. We also have the culture instability when we have concave walls, and all of these things have different physics. And that's what we need to understand, all these different modes to be able to model transition in any scenario. And we also have no modal instabilities that are they are coming from the non-normality of the equation of the Navier-Stokes equations. And then in 3D boundary layer, we have those in 2D plus cross-flow instabilities, strict secondary instabilities, attachment line, corner flow, referencing instability. So we have plenty of different types of ways for the flow to become turbulent. And this is everything we need to understand to be able to have a reliable model. So in this presentation, I'm going to focus just in axisymmetric boundary layers. So it's just a 2D flow. And in this 2D flow, we're going to have oblique first modes, second planar second modes. We're going to have separation, instabilities, and also some non-modal instabilities can be important there too. Okay, so that's what we need to have been take into account to be able to understand transition for the current case. So the measurements, and using this model for this study is a cone-cylinder-Flare experiment. So usually how we do these things is we say, okay, there is a problem here we don't understand. When we have a corner and there is separation, how transition is in that separation. So then we design a model, in this case a cone-cylinder-Flare, in which we can isolate that problem, and then we do experiments and then computational analysis to try to understand the model, and then we can extrapolate to the real world. So these experiments were conducted in the Boeing Air Force Mach 6 quiet tunnel at Purdue University. And it's just at 0 degrees angle of attack, sharp 5 degrees half angle cone, followed by a cylinder, and then a 10 degrees half angle flare. Why it's important to mention this a quiet tunnel is because in this tunnel, the free stream to the model, so what is the air inside the tunnel, is super quiet and simulates flight. In conventional tunnels, that doesn't happen because you have turbulent boundary layers in the tunnel, and that radiates noise to the boundary layer. So then you can have a different scenario to what you find in flight. But in this particular tunnel, they are able to keep the laminar boundary layer in the tunnel, in the nozzle. So you have a very clean flow acting in the model that simulates the flight scenario. Okay, so this is a sketch of the same model. Is as I mentioned, is a cone-cylinder-Flare, and it's axisymmetric. The conditions for this study were 11 million per meter unit Reynolds number. It's a Mach 6 condition. The stagnation pressure for the tunnel is about 1 million Pascal, and the stagnation temperature of 421 Kelvin. These are the conditions, the higher Reynolds number conditions to run quiet in this tunnel. So what they did in the experiment is they have several wall pressure sensors, all these points here in the model, and those are PCBs and Coulomb sensors. They also did FLDI measurements of the density profiles. So you try to do as much as you can to understand what's happening. So for example, on the left, what we see is from one of the PCB sensors, actually different PCB sensors along the surface. And what we see is that as we go from 0.38 in the blue, dark blue line here, we already see a lobe here, a distinct lobe that is coming from somewhere. And that's what we call flow instabilities in the boundary layer. As we move forward through the separation region that forms in this corner, then we start getting extra ones, and these lobes start to grow, change in frequency, and you also get these low frequency ones. And that's what we don't understand what's happening when we did the experiment. They also did accelerating, so you can even see the boundary layer and the shocks in this flow. And they also did heat transfer measurements, and that's where they started to see that they were getting some three-dimensional structures downstream of the flare. So around this here, this is where this window is, and they see these streaks after separation. So all of these things, what we can use for the measurements to understand the physics in this case. So the objectives that we had when we started doing this is to understand the origin of the distinct lobes measured by the wall pressure sensors. By distinct lobes, I refer to these lobes in this spectra, right? This is frequency horizontal line. This is spectra for the pressure at the wall. So these lobes here is that we need to understand what they are coming from. So for that, what we did is to investigate the instability characteristics of the boundary layer over the model. And we do the evolution, we study the evolution of convective boundary layer instabilities. Also, we did the global instability analysis to study the potential for self-excited disturbances in the separated region. And we also studied the effect of the nose tip radius and the flare angle of the instability characteristics. So there is always some uncertainty in the experiment to small changes. Also, we wanted to identify the mechanism for the measured streaks that I mentioned before. The streaks, by streaks, I refer to these striations here in this plot here, and by this azimuthal angle, so it's around the flare. So you see these striations here, what we call streaks. And to investigate those, we investigate all the possible mechanisms that we know from the literature doing similar things. So we study the evolution of three-dimensional stationary convective disturbances, the nonlinear interaction of oblique traveling disturbances, and also study a three-dimensional saturated solution for the globally unstable conditions, if we find any. So the strategy to do this is put everything now in the computer. We know the flow conditions. We have max X, same Fierstein-Reynolds number, and we set an isothermal wall of 300 Kelvin. That's the room temperature because the experiments run super quickly. So there is no time for the model to heat up. It runs only for 1-2 seconds. So we can assume that the temperature of the model didn't change at the surface. So what we do is we calculate an asymmetric solution using a subcapturing second order finite volume Navier-Stokes solver with shock adaptation. Then we run linear stability analysis, and that's, I will explain these terms, is we use parabolic stability equations and the harmonic linear Navier-Stokes equation for the evolution of the convective disturbances. We also do the global eigenvalue problem to study possibility for self-cited global instabilities. And we also use the harmonic linear Navier-Stokes equations to study non-modal stationary disturbances and the linear wall roughness forcing analysis. We are trying to see if there is anything linearly growing, anything that could grow linearly for this flow. Besides of that, we also did some nonlinear analysis using a higher direct numerical simulation solver for them to study three-dimensional solutions. And for that, we use this domain here in the black edges. So we just focus in the separated region for the three-dimensional solutions. For that, we study the nonlinear evolution of convective global instabilities. And just in the subdomain that I mentioned here around the separation region. The solvers we are using, the tools we are using to do this study, computational study, is the Vulkan CFD, a NASA solver. As I mentioned, it's a subcapturing second order finite volume Navier-Stokes code for the mean flow calculations. Then we also use a Guino-based high order DNS solver that has invisible fluxes with 7-order Guino, viscous fluxes with 4th order central finite difference scheme, has been validated for transitional and turbulent flow configurations in the group. And then for the stability analysis, we use the Mafia solver. It's matrix forming instability analysis. It's a multidimensional model and non-modal stability analysis solver. It does linear stability analysis based on eigenvalue problem for 1D, 2D, and 3D flow problems, and linear and non-linear PSE for 2D and plane marching PSE for 3D flow problems. And also the harmonic linear Navier-Stokes equation, as I mentioned before, for non-parallel 2D and 3D flow problems. So with this tool, what we are trying to understand is all these instability waves that can grow in the laminar flow and lead to transition, as I mentioned in one of the first slides, right? All the mechanisms can be studied with this stability solver. Starting with the theory. So what we have is now is the laminar flow, the laminar boundary layer. In this case, let me just point at it, is just this solution over the cone is asymmetric. So we just use that as our laminar flow. That is what we call Q bar. So that's that solution from Vulkan. And what we're going to study is these infinitesimally small perturbations to that flow. Because the flow is asymmetric and is not dependent in time, we exploit that, and then we separate, we do Fourier in both, in time and in the azimuthal direction. So we have the laminar boundary layer, and then we impose those perturbations in top of that. Something we do in PSE is to exploit this slow variation in the stringwise direction. So when the boundary layer, we have boundary layer, they are slowly growing in a stringwise direction, and then we can assume this separation of scales, and it's just to make the calculation much more efficient. That's the only thing different. So instead of solving for the purple line, that we need many points to solve this wave, we just solve for the red line here. So we need very few points to solve that. And how do we predict transition? This is the most typical method from the 50s, I think, is the n factor method. and it's already used for aerodynamic design calculations. So the transition onset location is predicted as a certain factor that we is a semi-empirical method because we obtain that critical value from correlations and experiments. So for a boundary layer, we have horizontal axis is the stringwise direction from the nose of the cone, for example, or is destination point or the leading edge in an airfoil. As we move downstream, the local Reynolds number increases and the flow becomes more unstable. At some point, you will increase the unstable branch. So from this point to this point, we'll have unstable waves that linearly grow. This growth is what we quantify as an n factor term. It's just the logarithmic ratio of that growth, amplification growth. And that's what we use for transition prediction. That's the n factor envelope. So for each wave, each frequency, and each wave number, we calculate that n factor, and then we just calculate the envelope of all those lines, and we have the n factor envelope. And with that, we know what's the critical value for transition. Let's say, for example, 9 is here, and then we know what's the predicted transition location for the modeling. How we get to that, there are different theories. The simplest one is the Sommerfeld linear stability theory, quasi-parallel theory, in which we assume parallel flow at each stringwise station. So we just take all the derivatives with respect to the stringwise direction equal to 0. That's C refers here to stringwise, eta to wall normal, theta to azimuthal direction, and t to time. And we also take the wall normal velocity equal to 0, and then we can build an eigenvalue problem. And this is what is commonly known as Sommerfeld, as many people do. So for each wave number and beta, now we can get the growth, an eigenvalue, and the imaginary part of that eigenvalue is the growth rate of that mode. And with that, we can calculate the factor. Okay, so that's the 1D eigenvalue problem. But in this case, all the theory I'm using here is for non-parallel flow, and I'm taking into account these effects in the solution. So we can use either the harmonic linear Navier-Stokes equations. They still exploit the basic state independent with respect to time and azimuthal direction, but we solve a full two-dimensional system of equations to solve for this purple line. However, when we also assume that the flow has a slow spatial direction in X, or in the stringwise direction, then we can use the PSE or parabolic stability equation. But at the end, we get the same solution, either with more points or less points. It's just that it's faster. We also did, for this analysis, some non-model analysis, and for that, what we do is an optimization problem. I don't need to go too much into this, but we use the variational formulation using direct and adjoint equations to know what's the optimal perturbation for maximum growth. We do this when we don't know what's happening, so we are trying to see if anything can grow linearly in that flow. And also, another method that we have used for this is the global stability analysis. So, for example, we have separation or a cavity. The flow is super non-parallel in that region, and that can trigger global instabilities. And for that, we solve actually the same equations of the HLNSC, but with complex frequency. So the real part is the frequency, and the imaginary part is the growth rate of the disturbances. So in this case, if we get a mode that is unstable, that mode means that it's going to grow in time, and it's going to dominate the instability of that flow. So, okay, so now I'm going to start with the results using all those things I just mentioned before. So starting with a symmetric laminar flow. For this thing, we use Vulcan, the NASA code, all the conditions I mentioned before. And then we compare with the experiments, because in the experiments, they were measuring the heat transfer in the flare region. So this is the cone region, cylinder region, and flare region. This is the stringwise direction, and this is the heat transfer. We calculated the flow solution for different wall temperatures, 280, 290, 300, 310 Kelvin, and 320, and then compare with the experiment. And then we realized that we had a very good agreement for 300, so that's the temperature we use for the wall, for the remaining of the talk. But still, we had not a very good agreement in this region here, and that's where separation is happening. Separation starts in this line in the cylinder, and the flow reattaches at this line. You can see that the solution and the experiments agrees very well after reattachment, but not so well here in the separation region. That's something we still need to further understand. Now, this is the map contours for the flow over the cone cylinder flare. And you see there is something here happening. It's a much thicker boundary layer. So the boundary layer is this blue color green here, very close to the wall, super thin. But then here you have super thick boundary layer. And this is a zoom view of that with streamline. So you can see that the flow is actually turning back in this region. So that's a separation bubble, a separated bubble. Also here at reattachment, we have what we call the reattachment shock. That is super clear here with this change from orange to red. So because of the supersonic flow, we get shocks when the flow is changing direction. Actually, since I mentioned they have oscillated measurements, we can actually do a direct comparison with the flow, the boundary layer, and the separation shocks and reattachment shocks. And what we did is just put the isolines for density on top of that. And you can see that the solution agrees very well with the measurements. So the location of the separation shock, the edge of the boundary layer, and also the reattachment shocks agree very well between the calculation and the experiments. So now is when we use that solution to do analysis, and we start with the evolution of convective instabilities. So for that, I'm using the PSC in the cone region, so I can get the growth of instabilities from the neutral location. Remember that first figure with that neutral curve. So all the modes that grow here with PSC, and because here we have corner separated flow and all of these, we cannot use PSC because we cannot assume that the flow is slowly varying in the streamwise direction. We have strong variations there with separated flow. So for that, then we need to use a much computationally expensive method like this harmonic linear Stokes equations. So what we do is, again, run PSC up to here, then we know all the instability modes that grow in the cone, and then use that as an inflow for the HLNSC to know how those disturbances are evolving in this region. And then again, we compare with experiments. So the black line here in this plot is the spectra from the PCB. The PCB is located at this black line that's going to move for all the different sensors. So we are going to be comparing the results with the different measurements at different locations. Since the analysis is linear, we need to normalize it with some amplitude. So what I did is to select this 7.4 10 to the minus 11 to match the measurements at that initial sensor location. So here, this peak is, I selected this amplitude, initial amplitude, to match this peak with the experiment. And from that point, we just use the predicted amplification to compare with the measurements. Here on the left, I have the real part of the stringwise velocity of these perturbations, so we can see how they evolve through the separated region here and then in the reattachment. So here, we are just focusing in the cylinder and flare region with the separation. This is for 60 kilohertz with a azimuthal wave number of 20, so a three-dimensional perturbation. And this is a two-dimensional perturbation, m equal to 0, with a frequency of 210 kilohertz. So now we are going to start moving through all the different sensors to see if we agree or not with the measurements, so we can explain what they were measuring. Here on this plot, I'm having all the planar and also oblique waves. So M, remember, is the azimuthal wave number of the disturbances, and the horizontal line, I have the frequency of the disturbances. So for each frequency and each azimuthal wave number, we need to run the PSC and the harmonic linear Stokes equations to know to calculate the evolution of the disturbances. So now moving through the sensors, now we are inside the separated region, and we see that they were measuring no instabilities there, and we actually see that the prediction is that all these the disturbances are below that threshold. So we agree with the experiments there. And now as we move forward, we start to measure some lobe here in the low frequency branch that was not existing before separation, and also this high frequency one that is super similar to the one before separation. And actually from the calculations, we also have this low frequency lobe and this high frequency lobe in the calculations too. And as we move forward, we actually see that there is a quite good agreement between the measurements and the calculations with these two lobes, low frequency one for these oblique disturbances, and the higher frequency one is also oblique, but also planar is there. So when we keep moving, we see there is some extra lobe that we calculate, but also we agree very well with the measured peak. And as we move forward, they actually also measure that second peak. So it seems that what we are seeing here is actually a quite good comparison, because this was applied comparison. We are not using the experiment just to set up the initial amplitude and then see we are predicting the same evolution of the disturbances. By the final measurement, we see actually a very good match of the prediction and the measurement. So now we can say that these oblique low frequency waves are amplified along the shear layer of the separation here, and that's why they measure them in the measurement. So now we understand what are the physical mechanisms for those measurements. We did the same thing with the Coulomb sensors, but we got actually a very similar conclusion. As you can see now, as we move through the Coulomb sensors, they are again capturing both lobes at those locations with the Coulomb and with the PCBs. All right. So now what we also plot here is just the M-factor envelope for different configurations. As I mentioned, we're going to study also the effect of the flare angle and the nose radius. So what these plots are showing is the M-factor envelope for all the different disturbances, planar and oblique with different frequencies. For the same configuration of the experiment, that's the 0.1 millimeter nose with a flare of 10 degrees. That's the blue line on the left for planar waves and on the right for oblique waves. And then we change flare angle, we reduce it to 8 degrees, or we change the nose radius to 1 millimeter. What we see is that reducing the flare angle reduces the amplification in this region, in the separation region, for both the planar and the oblique waves. And by increasing the nose radius, we get a stabilization of the waves in the cone. The cone is up to 0.4 for both planar and oblique waves. But then we have a different effects in the separation region. Actually, the oblique waves have more amplification there. If we just move these red lines up, then we can do a direct comparison with the previous one. So the effect of the nose radius is just mainly to stabilize the disturbances in the cone. Now we can also compare with other experiments performed at the University of Maryland. In this case, this experiment with a cone flare model. So we are just trying to see if the same kind of things are happening for that case, and actually it's true. But they observed in that case, doing some SPOD analysis of the measurements, was that the high frequency waves that they observed in those experiments through the separation and reattachment, they kind of, for the high frequency one, they didn't grow there, they just stay constant in amplitude, and then they start to grow again at reattachment farther downstream. But actually the low frequency ones, they grow through the separated region. And that's actually the same thing we get for the cone-cylinder-flare. So that seems to be common for those two models. So now we have a better understanding of what's happening through separation for these waves, and that's something we didn't know before. We also did global instability analysis of these configurations, because in the separation, we can have waves that grow by itself. So it's not something that comes from the cone, but it's actually emerging itself in the separated region. And what we have here is just as changing flare angle from 8, 10, and 12. And we see that the modes become unstable around 9 to 10 degrees. This is the growth rate of the disturbance, and this is the azimuthal wave number of the disturbance. So 0 is for 2D disturbance as symmetric. Larger than 0 is three-dimensional disturbances. So for the 10 degrees with M equal to 6, that the peak is here, we have this very long wavelength mode that is all over the separation region. The dashed line is the edge of the U equal to 0 isoline. So this separation and reattachment are here. And for the just 10.3, or we could plot also the 12th case, we have a much shorter wavelength. So higher azimuthal wave number is shorter wavelength mode that focus just in the reattachment region. So we have a clear separation between the 10 degree to higher than 10. So to understand that, we also did different calculations for just changing by 0.1 degrees the flare angle, and we saw there is a sudden change at 10.2 flare angle, and we go from the long wavelength mode to the short wavelength mode. So the physics are going to change at that degree specifically, and that the flow becomes globally unstable for 9 degrees. So the case of the experiment for 10 degrees was actually globally unstable. And this unstable mode for 10 degrees was also found in a Mach-5 flow over a slender double wedge by other group. And actually the maximum growth rate was found for the same wavelength to separation length of 0.26 for both configurations. So even a slender double wedge or a cone cylinder flare had the same global mode for when it becomes unstable. And the effect of the nose-tip blackness was just to stabilize the separated flow. It was very notable for 10 degrees half-angle flare. And so in this plot here, this dashed dot line is for the blunt case, while the other are for the sharper case. So what we see now is that for the experimental case, 10 degrees, we have the peak around 5 and 6. But they were measuring disturbances in the experiment of 36. So this is much smaller than that. So we still don't understand why they were measuring those streaks of m equal to 36. And that's what we want to understand in the second part of the talk. So we want to understand the origin of those m equal to 36 streaks. And for that, what we did is first, as I had just presented, is see if the globally unstable mode had that azimuthal wave number. That's a no. And then we look at the convective stationary perturbations, because previous studies have shown that that can be one reason for that. We also look at the nonlinear global mode temporal evolution to see what could happen in that case. And also we look at the oblique max first mode nonlinear interaction. So those waves that I mentioned before, the low frequency waves that grow through the separation region, they can interact between each other because they're oblique and create stationary modes. And that's something that was reported also in a JFM paper recently for one cylinder flare case. So okay, so let's start now with the convective stationary disturbance. For this, we did optimal growth for nonlinear analysis and also linear localized wall roughness forcing analysis with the harmonic linear Navier-Stokes equation. So for the optimal growth, we are trying to see what's the optimal perturbation is that is super broadband. So there's not a clear indication of m equal to 36 in this analysis. And something similar we got with wall roughness forcing, because sometimes we can argue that optimal growth cannot be physical. So we just study wall roughness forcing before the cylinder to see what are the waves. And actually, what kind of similar results. We have a broadband amplification of stationary disturbance, convective disturbances, extending up to m equal to 150. So this does not explain the measurements. Next, what we did is, okay, no, we know that for the experimental condition, the flow is globally unstable, so there is a self-cited instability. So, okay, so let that instability to grow and see what happens. So for that, we use a high order DNS with the azimuthal wavelength equal to 60 degrees. So this is this black box here. So that's the m equal to 6, the mode that we found before in the analysis. So we start the simulation in time with a symmetric solution plus an epsilon of the global mode. And that epsilon was set to 10 equal to -5 to have some linear evolution. So what you can see here on the right is a different probes inside the separation, actually, over this black line here in the separation region over the azimuthal wavelength. We have the evolution of the azimuthal velocity perturbation, and we can see it agrees very, very well with the predicted growth rate of the global stability analysis. So this is kind of a validation of the analysis of the global stability analysis. But at some point, it stops growing and it saturates. So actually, we have a new solution. It's three-dimensional now. So the global mode amplifies with the predicted linear growth rate until nonlinear saturation happens here from this time. Okay, so now let's look at that solution now, because it has changed because of the global mode. Here I'm plotting just a zoom view of the Stanton. That's the heat transfer at the wall for 9.2 degrees flare angle and also 10 degrees. And what we see is a very strong difference between those two cases. Just the difference is just a 0.8 degrees difference in the flare. For one, we have a long wavelength modulation of the flow, but for the other one, we have a short wavelength modulation of the flow. So now let's look at the Fourier modes of these to see what happens. So if we look at the Fourier modes of that modulation, in U, we get that the mean flow distortion is very strong, m equal to 0. That's the 0 component of the Fourier mode of that 3D modulation. The fundamental one is m equal to 6. And then we have the first harmonic equal to 12. However, if we look at the heat transfer Fourier decomposition, what we see is that the mean flow distortion is bigger just after the cylinder juncture corner, and then we have the fundamental mode here to be dominant. But after reattachment, we get the M equal to 36 mode that was measured in the experiment. So suddenly, by an M equal to 6 global mode, we get that the maximum Fourier component after reattachment is equal to 36, and that's in the heat transfer. That's what the measurements were doing. So now we probably have the answer why they were measuring M equal to 36 streaks, and that's because of the nonlinear evolution of the global mode. And then we also look at the oblique max first mode nonlinear interaction. So for that, we use the saturated solution. And then we impose in the DNS with localized wall forcing at 0.26 in the cone, many different waves from 6 to 36 and different frequencies. So we can cover the full spectrum for the instability waves. And actually what we found is that the nonlinear interaction led to a streaky structure with M equal to 60. So again cannot explain the M equal to 36 streak that we had in the experiment. So just to conclude, I hope you understood everything here. So what to take home is that the instability characteristics of the boundary layer flow over the cone-cylinder-Flare model were studied. We found a remarkable agreement with the heat transfer measurements, but only downstream of the reattachment. The oblique disturbance with 31 feet to 150 kilohertz, that's what we commonly call the max first modes, amplify along the shear layer over the separated region and lead to the measured low frequency lobes. So now that's something we understand we didn't know before. And also the planar and oblique disturbance with 180 kilohertz to 150 kilohertz, and that's what we call the max second modes, are strongly stabilized in the expansion region, but begin to amplify again at the reattachment location and lead to the measured high frequency lobe. And then for the mechanism for the emergence of the measured streaks with M equal to 36, we first studied the optimal growth and linear wall roughness analysis to see if the amplification of convective stationary disturbances could explain that M equal to 36, but that was not the case. We also found that the globally unstable was a globally unstable flow with M between 5 and 6, so that cannot explain that M equal to 36. But however, when we studied the nonlinear evolution of that global mode with M equal to 6, we found that the saturated state had an M equal to 36 dominance in the heat transfer. So and that can explain that experimental measurements. And also we look at the nonlinear interaction of the max first mode waves that led to a streak structure with M equal to 60 that couldn't explain those. So now I just wanted to acknowledge the support of these studies by the NASA Transformational Tools and Technologies project of the Transformative Aeronautics Concept Program, and also by the NASA Hypersonic Technology Project. And also a couple of grants from the US DoD, one with the Air Force Office of Scientific Research and by the Office of Naval Research. And the computational resources supporting this work were provided by the DoD SPC-MP program in the US, the NASA NAS supercomputer, and also the NASA LarK cluster. And with that, we'll be happy to answer all the questions you can have or discuss anything about this.
Pedro, can you hear me?
Yes.
Pedro, can you hear me?
Yes.
It's going to be, for questions, it's going to be a bit confusing. But I have one or two questions for you. And I'll use my own computer. And people here in the room will listen to me as well. And o pessoal consegue me escutar na YouTube. So everybody seems to be listening to me. Okay. So first of all, thank you for your talk. I think people were able to learn that you studied something that's very complex and that you have very many tools, a suite of tools, which are also very complex, but you are able to predict many aspects of it. So we can see that the results match and all that. But I want you to explore for the audience, what's really the purpose of this research? Why predicted transition is so important in this, in rockets? I'll be talking about heat transfer and why heat transfer is so important in this rockets. Can you explore some of these for the audience, please?
Yeah, of course. So in high speed, so
eu coloco o microfone no alto-falante. Hold on.
so
No alto-falante do meu computador. Hold on. Pedro, say something just for me to be sure.
yeah, I'm here.
Sure that we listen to you. Okay. We can hear.
You can hear me?
Microfone pro meu computador. Meu computador. Okay.
So so currently, actually, current is still we can say that right now, even NASA, when we are, for example, designing a hypersonic vehicle, for example, when we have a re-entry vehicle coming from the space to the Earth, we need to know how is the flow over that vehicle, because at those super high speeds, the heat transfer is super high. The turbulent heat transfer will be 10 times bigger than the laminar one. And if we design based on turbulent flow, we will need to have much thicker and much heavier vehicles than if we were designing them to be laminar. So understanding the transition process and when the flow is going to be laminar or not, then we could actually save a lot in the weight of the vehicles, and then have a much efficient vehicles for flight and get farther, faster, and cheaper. So right now, transition is known to be a total breakthrough in design, actually also for aircrafts, but mainly for supersonic and hypersonic aviation, because you cannot fly something that is designed to be turbulent for too long, because it's super heavy to fly. So if we can get laminar flow technology to fly even aircrafts, and Boeing is already doing that with the new 787 and all these Dreamliner and all these aircrafts, they are adding natural laminar flow components, because you have much less resistance to fly and much cheaper flying, longer flight, and lighter vehicles. So that's one of the reasons why it's super important in hypersonics. Actually, more than the skin friction or drag to fly is the heat transfer, because 10 times more heat transfer. If we can design a laminar vehicle, we could carry more than two to 4 times more payload. And that's why it's super important to understand transition for these cases.
Did you say 2 to 3 times more payload? 2 to 3
2 to 4.
More payload?
Yeah.
You hear me?
Yes.
You hear me still? 2 to 3 times more payload.
Yes. Yes.
That's why. So if you can have a laminar rocket, you take 2 to 3 times more payload. Amazing. Another thing I was going to ask is, how about flight experiments? Can you get something from flight experiments? Have you been able to compare results with flight experiments? What can be measured in flight experiments?
Yeah, so there's been recently, there are very few flight experiments, but for high speed. But there were one called the HypersonicCone one. It's a circular cone, and they were able to measure just transition location, and then you run this same thing. You run axisymmetric laminar flow, and then you run PSC. You calculate the M factor, and they were actually able to correlate the experimental transition location with the calculation. So is that that was the first time that M factor was observed to work in flight for a hypersonic vehicle, and that happened like 10 years ago. From them, there've been 2 or 3 new experiments in flight conducted here in the US. Now with more complex geometries like the elliptic cone or the new geometry called bulb. that is kind of a concave wall thing. And those are being analyzed right now as we speak. And that's something that is nowadays there is a lot of effort here, at least in the US, to understand this, to be able to design vehicles knowing where transition is happening instead of just assuming the flow is turbulent.
Isso. Agora eu estou falando com quem? Com Pedro. Pedro, do you hear me still?
Yeah. Yes.
Anybody has a question? Alguém quer fazer uma pergunta? Também pode fazer. Ele fala espanhol também. Ele já tem pouco em português. Ele vai entender. Mas eu não tenho certeza se ele está me ouvindo. Pedro, let me know if you listen to me. Do you hear me?
Yes.
Hi, Pedro. Congratulations on your presentation. You use matrix forming to calculate that exams. It's not cheaper to use the backstep method.
So can you repeat the question, Marcelo? I got something about matrix forming for eigenvalue.
I couldn't hear you say it again.
That I didn't get the question. It was something about eigenvalue with matrix forming, but didn't get anything else.
Yeah. So he's asking, why do you use matrix forming rather than time stepping?
Okay, good question. In these flows, we are calculating a laminar flow, and then we use that as our basic state to do all these analysis I'm showing here. And so we have a 2D flow, and then we impose three-dimensional disturbances that we can calculate with this in Fourier. If we want to do time stepping here, we will need to do three-dimensional time stepping solver for this, but with doing matrix forming, we only solve a two-dimensional system, so it's cheaper in this case. Time stepping becomes very useful when you are trying to do analysis of 3D flows more than 2D flows. At least that's my understanding of the time stepping methods and how I see them to be super useful.
Curiosidade. All right. Pedro, my last question is, what's next? What is before my last question? Can you explain a little bit more about the computational tools that you use? How large are the simulations? What are the actual discretization that you use? Is it finite differences or for the DNS?
Okay.
How about
for the
DNS? Parallelization? Do you use CPU or GPU?
Okay. Yeah. So
what do you say about this?
Yeah, for this analysis, we use these three solvers. The first one is the Vulkan CFD. This is a NASA developed CFD code using finite volumes, cell center finite volume and Navier-Stokes code. So we use this code to calculate the mean flow with the SOC. So we have the SOC, and it has the ability to do 2D axisymmetric and also 3D flows. In this case, it's super handy because we can use the axisymmetry of the flow because it's zero angle of attack. So we have axisymmetric flow around that cone cylinder flare model. And then this uses actually just one or we run this with maybe 40 cores. So it's something small to run. This is super fast. It runs in a couple of hours. So it's not a heavy calculation. This is just second order. So that's why we put a lot of points. We put like 3,000 by 1,000 points just to be super safe to calculate the laminar solution. However, when we are trying to do the nonlinear evolution of disturbances, I'm looking at all convective waves now in 3D, then for that we use a high order DNS code because we need high order to be able to capture the evolution of the waves. You know, if you use low order for wave evolution, then you're going to have a lot of dispersion error, and you're going to need too many points, an infinite number of points. That's why we go for high order schemes with the invisive fluxes using the Wiener scheme. Wiener scheme is similar to finite difference, but you have a flavor of the up Wiener schemes. That's when you have shocks or discontinuities, you only use information to one side or the other, so you don't have problems with the numerics. And that's super useful for high speed because you can have shocks in high speed flows. And for the viscous fluxes, fourth order central finite difference is known to be good enough. For the analysis, we use high order finite difference in this matrix forming approach. And that's to be able to do PSE and plane marching PSE and all these things. I've been working with this now for more than 10 years and has been super efficient. We use a sparse algebra with MAMS solver. I don't know if you're familiar with MAMS. So thanks to the finite difference, the matrices are very sparse. So you can just put them in the MAMS solver and go running with them. They do multi-thread, and also you can even do multi-core CPU. All these solvers are CPU. I know there is an effort to port Vulkan CFD to GPU, but all the others are CPU only. And for the DNS, it's an explicit DNS solver, so it's super parallelizable. So you can use any number of CPUs. For the current simulation, probably we didn't use more than 5 or 6 nodes. Maybe each node has 24 to 40 cores. So it's not really a large calculation.
Okay. And what is next? I mean, can you can predict the transition, many aspects of the transition in the experiment, but how about the real vehicle? Is this enough to predict transition in the rocket?
Yeah, so that's a very good question.
To incorporate.
Yeah, that's a very good question, because here we are just studying with these 10 degrees flare and things like that, in which the flow is starting to be unstable and you have all these waves coming in and everything, but we still don't have transition in this flow. So the next thing is to now look at higher flare angles in which the flow is super unstable, as we saw in the global analysis for 12 degrees. Let me show you that. So here, this 10 degrees is the red line. 0 is the threshold for globally unstable flow. When you go from 10 to 12, it just the flow becomes exploits. It's globally unstable, all these super broadband wave numbers. So the idea is to start looking at in those degrees and look at experiments together with calculations to see if we can predict how transition happens in the experiment. And then from there on, we should be able to understand the mechanics for transition in these kind of flows. So right now, they are doing experiments for 12 degrees.
Pedro.
Yeah.
So finally, I just would like to thank you again for your talk, for your time. People could see that you do very hard work, really, with a lot of competitions and complex stuff. So let us thank our speaker. We are applauding from here. And that's the end of our talk, on our session. Thank you very much. See you sometime in the conference, hopefully.
Thank you, Marcelo. See you soon. Bye-bye. Bye-bye.
Para engenharia, para conseguir resolver problemas de alto conteúdo tecnológico, né? Um dos aspectos que ele tinha falado é que o payload, quando você consegue manter o escoamento laminar, a ambição deles é conseguir aumentar o payload payload é a carga paga de um veículo lançador de satélites, então um veículo espacial. Para vocês terem uma noção, o veículo lançador de satélites do Brasil, aquele que nunca funcionou, a carga paga dele era 0,3% do peso dele todo. E era um veículo que não chegava a sair da órbita terrestre, né? Para mandar um cara para a Lua, ou para mandar um veículo fora da órbita da Terra, a carga paga ainda vai ser bem menor do que 0,3%. 0,3% significa o seguinte, que você tem que conseguir prever essas coisas dentro de 0,3%. O melhor do que isso, né? Porque assim, se você errar em 0,3%, significa que ou não vai funcionar, ou você pode levar um segundo de graça, né? E pagar duas vezes, cobrar duas vezes. Isso no veículo que era do Brasil. Esse aí é ainda mais sofisticado. Então, tudo o detalhe importa. Então o cara está tentando entender o detalhe mesmo. E por isso as coisas se tornam bem complexas. Bom, eu acho que deu certo no sentido que vocês viram que existe coisa sofisticada que precisa ter estudado, mas as ferramentas estão aí para quem está interessado no trabalho dele. Tulan, quem falar aqui? Passa agora para o Tulan para os comentários finais, vamos dizer assim.
Eu tenho um outro amigo que também está na NASA, que é responsável por aprovações de projetos, mas a oportunidade financeira foi maior. Está aberto, né? Um cara aqui de Araraquara, que está na NASA também.